All right, so let's get going here. At the beginning of this week, at the beginning of our discussion of kinetics, I introduced these graphs here, what we call free energy diagrams. And these are really popular ways to sort of illustrate information about chemical reactions, because there's a lot of information in just this little curve here, okay? If we look at the beginning point and the end point of this curve, right, the energy of our reactants and the energy of our products, we can get information about the thermodynamics of this reaction, right, whether or not it occurs spontaneously or non-spontaneously, because that just corresponds to the difference between these two energy levels. This gap here represents the delta G of that reaction. All right, so we can get information about whether or not a reaction is spontaneous or non-spontaneous from these graphs. All right, and again, that's just by looking at those endpoints. But there's also information about the kinetics of that graph in the very middle part here. In order for this reaction to go from reactant to product, it's got to jump over this energy barrier here. And the height of this energy barrier is going to be proportional to the kinetics of that reaction. We call this the activation energy of a reaction. All right, so the larger that barrier is, the harder it is to jump over, right? The larger the activation energy, the slower the reaction is, okay? So we introduced this kind of like qualitatively here, but there's actually a quantitative link between this activation energy and the rate constant for a reaction. All right, so this quantitative relationship is what's called, I can't always misspell this dude's name, the Arrhenius equation. All right, the Arrhenius equation tells us that our rate constant K is equal to some constant times E to the negative EA over RT. And that EA is our activation energy, right? The height of that barrier there on our free energy diagram. So we can see that our activation energy is related to our rate constant, right? K is our rate constant, through this equation here. And indeed, you could play around, plug in some numbers. You will see that if you put in bigger and bigger and bigger numbers for that activation energy, that K will get smaller and smaller and smaller, right? So again, the larger that activation energy barrier, the slower the reaction. And by slower the reaction, we specifically mean the smaller that rate constant. Remember, small rate constants are slow reactions, big rate constants are fast reactions. All right, R in this equation is just our go-to ideal gas constant, 8.314 joules per mole Kelvin. T is the temperature in Kelvin. All right, so then our last, so those are, so then our last missing variable here is this constant out front, A. We call this the frequency factor. Okay, and we'll do a little bit more of a deep dive of that towards the end here. Okay? But again, that activation energy on that free energy diagram, the height of that barrier we call the activation energy, and that activation energy is related to the rate constant for a reaction through this equation here. Okay? Now, let's remember about this rate constant. We spent the past like 2 class periods talking about these rate laws. all right? And we used a bunch of data, this initial rate data, to figure out our variables in these rate laws, one of which was that rate constant K, right? So by analyzing this data set, we found both the order of the reaction, but also that rate constant K. Okay, and again, that K is what we're talking about. This is related to the activation energy for a reaction. So what we're going to do is we're going to play a very similar game to what we did before in order to fill in the variables in this equation here. We're going to, again, have a data set that we're going to analyze. And by analyzing that data set, we're going to be able to figure out what that activation energy is, what the height of that energy barrier is. All right? So we're not going to look at the exact same type of data, okay? But we're going to do something very similar. What we're going to look at is the relationship between temperature, which is again in Kelvin, and our rate constant, K. Right, so I perform this reaction under a few different initial conditions, and I can do that analysis of my rate law to figure out what that rate constant is. Okay, so then I'm going to do it again, but I'm going to increase the temperature or decrease the temperature. I'm going to do the same process at a different temperature, figure out what K is. Change the temperature again, figure out what K is, right? And then I'll get a data set of temperature versus rate constant. So let's put down some sample data to work with. Okay, so first of all, looking at our data set here, let's just note, as temperature increases, what's happening to that rate constant? It's getting bigger, right? So as we increase temperature, our reactions go faster and faster. This should check out sort of intuitively, but also if you look at our Arrhenius equation, if you start putting in larger and larger values for temperature, you will get larger and larger rate constants. All right, cool. And again, our goal is to analyze this data to find our missing variables in this equation. And we got two again. That activation energy, but also that frequency factor A. So how are we going to go about finding our activation energy? Again, we're in a very similar situation to what we were in before, where we have this equation, but we have two variables that are missing here. Remember last time we played this game where we took the ratio of two data points because that allowed us to cancel out something that we don't know. We're going to play that exact same game here. To find EA, we're going to take the ratio of the Arrhenius equation for two data points. So by that I mean my Arrhenius equation. Holy cow, my voice is cracking all over the place. All right, Arrhenius equation, K is equal to A e to the negative EA over RT. So if we pick this first data point here, we have the temperature at that first data point and the rate constant at that first data point. Okay, but again, we're going to actually take the ratio of two data points. So K1 divided by K2 is equal to A e to the negative EA over RT2. So why are we taking the ratio? Why can't we just look at one data point? We got to play this tricky game where we take the ratio. Because what do I get to cancel out when I take the ratio? I get to cancel out that constant that I don't know, my frequency factor, right? So now I'm just down to one missing variable here. Because R we know, and T is part of our data set, right? R is just that ideal gas constant, so it's not really a variable in this equation. So the only thing I have is this one variable, so I'm down to one, so now I can just kind of plug in and solve. Okay. So how the heck do we solve for EA here? It's all trapped up in that exponent, all right? So how are we going to go about doing this? So first of all, we did this in the last analysis as well. How do we bring down an exponent? We got to use that function that everybody loves, or I guess it's an operation, that everybody loves from algebra, the log, okay? But now it's e to the power, so which one are we going to use, or so what are we going to have to use? The inverse of e is natural log, exactly. So now we're going to take the natural log of both sides. All right, and let me just zoom in here real quick because I want to make a point. Remember, my temperature is part of my data set, so I have different temperatures depending on my data points. So that's what my scripts come from there, T1 and T2, the temperature of the first data point and the temperature of the second data point. All right, so natural log of both sides. How does this help us out here? Okay. In the magical world of logarithms, log algebra here, which y'all can just trust me on, the natural log, of A divided by B is the same thing as the natural log of A minus the natural log of B. Okay, so we got to use this what the hell are they called? Identities here? Anyways, it doesn't matter. We could do it over here on the left-hand side. It doesn't really simplify anything for us, but we really want to do it on the right-hand side so we can get those e's by themselves. So this becomes the natural log of my numerator, e to the negative EA over RT1, minus the natural log of my denominator, all right, and this is great because, again, logs and e are inverse from one another. So this just effectively cancels out that e. So I get negative EA over RT1 minus negative EA over RT2. All right, and again, this is equal to the natural log of the ratio of Mackay's. And what is it I'm trying to solve for again? What are we looking for? The activation energy, right? So I have it in both terms here. So how am I going to get it all by itself? I'm going to, I don't know what it's called, the reverse of distributing it. I'm going to pull it out of both of those factors here. Right? So this would be the same thing as that activation energy times negative 1 over RT1 minus negative 1 over RT2. Right? I pull that activation energy out of both terms. All All right, this is definitely some of the ugliest algebra that we do all semester here, all right? But at this point, I believe in y'all. You can do it. Solve for that activation energy for me. Okay, I'll bring my data table down here as well, just to make it easier to see. All right, and you get a big number at the end, all right, just so you know. All right, so I'm just going to rearrange to solve for that EA. I'm going to plug in my temperature for T1, my other temperature for T2. I got my rate constant K1 and my other rate constant K2. All right, so I think the only thing to keep in mind, definitely keep that denominator in parentheses so you don't mess up your order of operations. You also got a bunch of minus signs to manage here. I just combined my two negative signs into a positive here. Okay, if you get a negative activation energy, something went wrong. Activation energies, unlike free energies, which can be positive or negative, activation energies always positive. All right, so if you got a negative number, go back and relook at your work here. So what I get is an activation energy of 44,000. Okay, so we got a big number here. If we look at why that might be, remember what our units for R are. They're in joules per mole Kelvin. All right, so this value that I got here for my activation energy is in joules per mole. Much like free energies, it's a little bit more natural to look at these in terms of kilojoules per mole. So 44 kilojoules per mole would be my activation energy. All right, so this is a very similar game to what we had to do before. We had this equation here, the Arrhenius equation this time, and we had this data set of temperature versus rate constants. We got two variables in that Arrhenius equation we're trying to find. So what we're going to do is we're going to take the ratio of two of those data points, because that gets us down to one variable, and plugging in all that information, first doing some algebra gymnastics here, and then plugging in that information, we can finally arrive at what that activation energy is. All right, so now we have one more variable to find in our Arrhenius equation here. Now we want to find that frequency factor, A. All right, but now let's look at our equation and what we have here. We're trying to find A, right? That's our goal. Well, what else do we have in this formula here? We always have R. Do we have a temperature anywhere? Yeah, that's part of our data set. We got both the temperature and a rate constant. And now we also have that activation energy. So now I'm down to just one variable, so I can pick one data point and plug it in and solve for that one missing variable. All right, so everybody take a second using our equation here, solve for that frequency factor using any one of our data points from our table. And again, you will get a very large number. You have to square away your units of energy. So you could either convert R to kilojoules, or you could just use the 44,000, the units of joules, right? But absolutely, make sure your units all square away for energy. We don't have to do a ratio anymore. The ratio trick is to cancel out one of our variables. Now we can just pick one data point. You can pick any one of those three data points, and that will be fine. I'm going to pick this last data point just for the fun of it. All right, and this over here might look scary, e to the negative 44,000 divided by whatever, but that's just a number, right? E is just a number raised to some power, okay? So I can just take both sides and divide it by e raised to that power. And again, I get a big number. I'm going to put it in scientific notation here. Okay, and so I get a frequency factor of 3,4,99995, or 3.5 times 10 to the 6. All right, so before we move on here, I just want to take a second to stress, I know it seems like we're doing a lot of pain in the butt algebra here. We learned how to do this for the rate laws and now for this Arrhenius equation. But there's a considerable amount of overlap between our approaches for those two things, right? So if we can kind of file them together in our brain in the same place, that'll be helpful in remembering it. In both cases, we have some equation where we're trying to fill in these missing variables. And in both cases, we have two variables that we're trying to fill in. And of course, we can't do algebra with two variables. So the first thing we're going to do is play a trick where we take the ratio of two of those data points. That gets us down to just one variable, so we can solve for that one variable. And once we have that, we have everything we need to just plug in and solve for that last variable in our original equation. All right, so in both cases, whether we were analyzing rate laws or the Arrhenius equation, from an algebra standpoint, we had a very similar strategy. Okay, and we said we got a big number for this frequency factor, and that checks out. Frequency factors in general will be a large number. So let's talk a little bit more about this frequency factor here. So this frequency factor, A, has two components to it, what we call P and Z. Z is the collision frequency. Okay, and this is an important sort of subtle point to mention about chemical reactions. Why do reactants get converted to products? Because they're flying around in the container, and eventually two reactants will smash into one another, and then they will react to form products, right? So collisions are a very important part of a chemical reaction. Reactants have to collide with one another in order to form products. So part of our frequency factor here is a measure of collision frequency, right? Just simply the number of collisions that occur in a given period of time, per second, right? So how many times are molecules colliding in our sample per second? And this is a big number. Molecules are moving very, very fast. Okay, so this number right here is going to be a big number for gaseous reactions. Z tends to be on the order of 10 to the 9. So what is that? 100 billion collisions per second for a gas phase reaction. Okay, the other component of this frequency factor here, P, this is what we call the orientation factor. The orientation factor is the fraction of what we call effective collisions. All right, it's a fraction, so it's going to take on a value between 0 and 1. So what the heck do I mean the fraction of effective collisions here? Okay, again, reactants are smacking into one another. That's how they form products, right? Well, it turns out that not every time a reactant collides with another reactant, it actually turns into product. Sometimes the orientation at which these reactants collide is very important. If they hit like this, there's no reaction. If they hit like this, there is a reaction. All right, so the way in which molecules collide, not every collision is going to be an effective collision, is going to lead to product. There's an orientation factor for these collisions. So if we look at this simple example here, we have these two reactants that are going to collide to form product here. Okay? Our product here, this chlorine gas that's going to form, well, that's not going to form if two nitrogens hit each other. That's what we would call an ineffective collision, no product. It's not going to occur if a chlorine hits a nitrogen. No, not an effective collision. But if the two chlorine ends of this molecule do collide, then check. Then we'll have our product that's formed, right? So the bottom line is there's only a small subset of collisions that are going to be effective collisions, that are going to lead to product. And that measure of what fraction of collisions are effective, that's what we call the orientation factor. All right, so what fraction of these collisions actually lead to product? So those are our two components for A. Both how many collisions happen in a given unit of time, but then what fraction of those collisions actually lead to product. Those are our two components here. Okay, just to say a little bit more about this orientation factor here, it varies for reactions. Okay. For perfectly spherical reactants, like single atoms, if it's a sphere, then all of a sudden it doesn't matter where you hit it, right? So this would have an orientation factor of 1, or a very large orientation factor. Okay? And generally speaking, the larger and more complicated a molecule is, the smaller and smaller that frequency factor becomes. So for very small spherical reactants, P is 1. Large reactants will have smaller frequency, orientation factors. Okay? It tends to be, the bigger a molecule is, molecules tend to have like one little site where a reaction takes place, right? So if you're a big molecule, it's harder to hit just that one perfect little spot. Okay, cool. So we found A for this reaction here. So let's just say for a gaseous reaction, A is equal to that 3.5 times 10 to the 6. What is the orientation factor for this reaction? Okay, so we can get at a good value, a good approximation of what fraction of collisions are effective for this particular reaction because it's a gaseous reaction. So we can go ahead and plug in 10 to the 9 for that Z component. So plugging in, we got A equals P times Z. Plugging in what we know, 3.5 times 10 to the 6 equals that orientation factor times 10 to the 9. All right, we've done a lot of pain in the butt algebra today. This is not one of them, all right? I believe in y'all. Tell me what that orientation factor is. All right, so our orientation factor for this reaction is 0.0035. All right, so that's the fraction of effective collisions. We like to think of things in terms of percentages. I don't know, the world has trained us to think of things in terms of percentages. So this is the same thing as saying that 0.35% of all collisions that occur in this reaction are effective collisions, actually lead to product. Okay, so that orientation factor multiplied by 100 will give you your percentage, thinking about this not as a fraction, but as a percent. Cool, all right, so just to rewind here, summarize. We have these graphs, these free energy diagrams. We like to use them to talk about chemical equations here. They're these curves. And importantly, the height of this barrier here is what we refer to as the activation energy. If we have a chemical reaction that we study, we can do it under a bunch of different temperatures. And we can use that data to solve the Arrhenius equation and figure out what that activation energy is, what the height of that energy barrier is. We also have this frequency factor term in here, A. We can have, use the same set of data to find out what that is as well. And importantly, that frequency factor has two components to it. What we call the collision frequency, how many collisions happen per second, and then the orientation factor, what fraction of what fraction of collisions are actually effective collisions, actually lead to product. All right, so by analyzing that data, we find out what that frequency factor is. If we know our collision frequency, which we do for gaseous reactions, then we can figure out just what that orientation factor is, just what fraction of collisions actually lead to a product. All right, that's all I got. Cool. We do have a little bit more to cover for this kinetics chapter, but we're not going to dive into that with like 8 minutes left here. We'll save that for Monday.